So now the next thing is, suppose you're unlucky. So your assumptions are violated. So you're unlucky. What do you do then? So we were quite happy and lucky that our assumptions were sort of well behaved. No issues with homogeneity variance. Quite nice looking normal distributions. What do? So you can do non-parametric tests. And so, as you remember from when we talked about t-tests, these do not assume normality. So but they are less powerful because the issue is that you sort of lose information. So by making things continuous and treating them as normal, you gain information. But if you don't do that, then you're going to have some issues. So there's many options, and you can read and find others. So I'm just going to run to some. There's a package called WRS2. And this does a one-way ANOVA for the trimmed means. So in that case, you trim the mean, so you take away some type of thing. So it's not fully non-parametric, but basically it uses some correction for the means, so for example, to adjust for outliers or in some way. And this function also doesn't require homoscedasticity. I always trip on that. Homoscedasticity or homogeneity variance. They're the same thing. It's basically the degree to which variances are unequal between groups. And you can get Lincoln. If you use that, you get the post hoc test. So how would you go about doing this? You do the same type of thing, and in this case, you would get the same type of conclusion. It's also significant, which is non-parametric test, and it will give you some estimate for an effect size which corresponds to this non-parametric way. Yeah. So it's quite similar to what we had before. It's just T one way for a one-way ANOVA. So you can also do it for with a bootstrapping way. So this is now does it 10,000 times. So remember our friend bootstrapping from when we did the t-test. So in this case, it will do bootstrapping, and it will again give you some statistics. So that's a more robust way of doing the same thing. You can remember you can take any statistic and basically apply bootstrapping to it, which is effectively trying to see how robust your findings are. Yeah. So same type of thing. The only thing is that we change this to BT. And we say how many bootstrap samples it has to draw. In this case, 10,000. Just pick a large number and pick how long you want to wait for it, because it's basically the computer doing lots of computations. So one way is to use the trimmed means. You could also use the medians. So rather than taking some of correction for the mean, you could use the medians. You cannot have many ties in your data set because that will cause computational issues. So if you have many values which are the same, then you have some issues. And this is how you do a medians type of test. In this case, it's not bootstrap, where we say how many iterations it has to do, and it's met one way. And again, we get the same type of conclusion. So it's not 0.0001 anymore, but it's still highly significant. So whichever way which you would have tortured your data, you would have found a group difference between the groups in this case. Yeah. So the analysis of medians also here leads to the same conclusion. So if you're really, really worried that you didn't spot your normality or so that there was some type of issue, you can always resort to these type of things, and hopefully all the tests will give you the same statistical conclusion. Yeah. And you can read through this WRS2 manual to find out more about how you can change some of these functions or tinker with these tests. Another favorite one of mine is permutation tests. Permutation tests are not the same as bootstrap. So basically, the premise is you have your spreadsheet, and we can shuffle that over and over and over and over. And if we have a small spreadsheet, we can still have the computer do all the possible combinations of your spreadsheet. If we have a very large spreadsheet, then we won't be able to do that. And so the question is, if we did those random shuffles of our data and we still get significant results, then probably it's not a robust type of effect. Yeah. So if we can do the same test over and over on our shuffled data versus actual data, and then see how often we get the same result. And so in this case, you also don't have statistical power issue because it's determined by your data frame. So shuffles are not the same as bootstraps. There's a difference. With the bootstrap, we sample from a distribution and we put things back. Yeah. And some assumptions still do apply. So for this permutation test, imagine if we didn't have independent observations, like all the kids or all the participants come from the same school or same university. That's creating hidden confounding, and permutation tests will not solve that for you. But it's quite powerful. So you can read more there and there. And this is how you do a permutation test. So basically, the premise here is that you can ask the computer to shuffle it over and over and still see if in your real data you would find the effect but not in the shuffled data. Yeah? And you can read more about how these tests work by looking at this. I just think it's quite a neat way to think of your data. You don't have to make any assumptions about normal distributions or parametric distributions. It's just your data, shuffling it around, and then seeing what happens if you had done that. Yeah? So a sample write-up you would do is you would say a permutation test by the coin package showed that there was a significant significant differences between the three groups, and then you report out max t type of thing and the p-value that you have there. That's how you would write it up. You cannot typically have post hoc tests for these type of designs, but you can get them via some other packages. Again, look at this if you need this. Like some of these things I'll just say, here's a package, go and explore more on your own. Any questions so far? So everybody sort of understands the premise of a permutation test. So basically, you can think of your Excel spreadsheet and shuffling the data about and then seeing if your actual result is different from all the shuffled data. So quickly moving on to ANOVAs. The difference is the C. You should sort of know what the C stands for. It's for covariate. So often you want to control for something. So you might want to control for, you might have a, you want to control, you're looking at a weight loss drug, and you could analyze the participant's weight at the end of the trial, but you might want to partial out their starting weight. Yeah, so you might want to control for the starting weight when they go into the trial. So this would be an ANOVA scenario where you want to control for a covariate which might influence how effective your manipulation is, for example. But you should be aware that this also can lead to all sorts of funky statistical issues in terms of confounding and false positives, and you can click on that link to read more. You should also be aware of something which is called horrendously Lord's paradox. It's something which you might not encounter, but imagine you have researcher one using independent t-tests on the difference scores, so pre-weight, post-weight, and then a test for the manipulation, and another person running an ANOVA. They will not get the same conclusion, which seems counterintuitive, but trust me, if you follow the maths through it, they're making different assumptions as to how the data behaves. Yeah? So you can read more about Lord's paradox, but don't expect the same results. So if you have researcher one who subtracts the post-weight from the pre-weight and then does the independent samples t-test, and you have somebody who does an ANOVA with the post-weight as the dependent and parsing out the pre-weight, and using the drug as like the between subject factor, they won't necessarily get the same conclusion, and it has to do with the different assumptions that go into ANOVA versus independent samples t-test. So that's quite shocking perhaps to some, but yeah, so don't be surprised if you ever encounter that. So the important thing also to remember is that R cares about the order in which you put things into your ANOVA. So you could have something, so LM uses type 1 errors, so the order in which you put in this, like extroversion first and then the group factors. So in this case, we're first controlling for extroversion and then doing which group they're in. You will get different, you can get different results depending on what you put in first. Yeah? So I won't flip between those two things, but these things start swapping around, and these things start swapping around in terms of F values and P values. Yeah? So that's because it's type 1 sums of squares, and type 1 sums of squares is the default for R, not for SPSS, and it will care about the order in which you put in things into your equation. So I'll talk to you slightly more about those type of errors later, but there's type 1, type 2, and type 3 errors. For now, you should know that the type of errors matters, and you can read again more about the links that I put in there. SPSS uses type 3, and so we can try and emulate that. I'll leave it for you to say whether that's always optimal, but that's the default from SPSS. So if you're a supervisor that wants SPSS style results, as soon as you start putting in things, you have to care about type 1, type 2, and type 3 errors. Yeah? Everybody with me so far? And it's basically to deal with the order. So what we can do is we can call car, and we can say it's a type 3 type of error, and then it will take into account we need type 3 errors, and then it should replicate what you get in SPSS. Yeah? The other one takes into account the order, and I'll explain how this works in more detail later. And so this just does the contrasts, which you might also want to include. Okay, everybody with me so far? So this was to get post hoc tests. we use multcomp, and then it's post H, GLHT, and then linear factor, MCP, and then Tukey. So again, a bit of code to do those multiple comparisons afterwards. So this is how you do multiple comparisons for the ANOVA type of things. And again, the default is the Tukey. If you need to do all sorts of corrections, you're going to have to look back at the manual to do Bonferroni or SIDAC or all these other corrections. So again, these are the type of tests you will get if you do post-hoc comparison. So this is telling you, is the differences between groups significant? Yeah. So a write-up of that would be a one-way ANOVA was conducted to compare openness to across groups whilst controlling for extroversion. Because remember, we put in extroversion now. There was a significant effect of cultural group. In addition, the effect of the covariant was also significant. And this is again how we report it in an APA-style type of write-up. Yeah. And then you would, if you would go beyond that, you would describe the post-hoc differences, and you could also then discuss whether this relationship between extroversion, because we haven't talked about whether it's positive or negative, how strong it is. You could try and illustrate that with a correlation or with a plot, for example. Yeah. So again, for most of these things, we have non-parametric alternatives. We can look. You can look at the LMPerm package in this. So if you need to do, if your assumptions are violated, again, for some of these things, I'm not going to run you through all the possible scenarios, but you're going to have a look for yourself. Now, the next bit is MANOVA. So sometimes you will have more than one dependent variable. You remember that scenario? Yeah, you might have heard MANOVA as well. So with a MANOVA, we have all the previous assumptions, and we have multicollinearity. And what we need to have is multivariate normality also. So not only do we need to have normality in one, but also all these other things need to be multivariable normal. And we need homogeneity of the covariances, not just of the variances, but also of how things covary. So how do you go about testing those assumptions for MANOVA? You use a multivariate Shapiro test. So you remember the Shapiro test was just the one you did for one. There's a bigger brother, the multivariate test. And this is how you do it. Again, you should bear in mind that it's sensitive to sample size. Larger samples, more easily significant. And so in this case, you would see that it is significant. Statistically, but it's only just scraping by. So I wouldn't be too concerned just yet, because you have quite a big sample, and this will be very easily significant. And I'll show you in a bit, but you can also then try and plot and see how bad it is. There's a whole host of other alternatives, and one you can do is the multivariate norm thing, and this will use skewness and kurtosis. It will print you some values, and it will say, yes, no, this is a problem. Yeah, and so in this case, it's spotted a problem with kurtosis. So remember, platykurtic, leptokurtic, so that's an issue in this data. And it will print you the univariate normality type of thing here. So is there an issue? Oh no, I think it's the opposite. So this one is supported, and this one is violated. Sorry. So you have an issue with skew here, and not with kurtosis. You can see based on the significance. So yes here means upheld. Sorry. And so it will do this for every single thing also to see if this is violated or not. And then it will also print all the descriptives, which I haven't printed here. Yeah. So important to bear in mind, yes here means good news, and the p-value means bad news. Yeah. And the nice thing is that it will also print some type of plot, which will allow you to assess how bad it is. So again, you can sort of check graphically. In a perfect world, all of these would be close to the line. Yeah. So there are some issues here in the sense that, again, if you go back to your stats, you might remember Malanova's distance, and this is chi-square quartiles, I think. So this basically tells you how bad the deviations from normality are. In a perfect world, all of these should be on the line. You could see some deviations, and especially here, there's sparse data, but these are really extreme cases. There are cases which are very far away from, if you think of your space and a centroid, there are cases which are really, really far away, so they're really outlying cases. So we wouldn't expect them to be very close to the line to begin with, because they're quite extreme. So it can be way worse. So if you found like a thing looking like this, or it's entirely zigzagging spirally but around this line, this would be quite terrible. But most of the data seems to be relatively close to the line, and it doesn't seem to be systematically biased in one way or another. So sometimes it's above here, and sometimes it's below. Towards this end, we're more below than above. So it is bad in the sense that if you take a significance test, it will be violated. But this, if I see this type of plot, I would still be fairly happy in the sense that it's not swaggering all the way around, and it's not like it's going like this. Alex can show you some of her plots which she had before, which were way more extreme. So so it's bad news, but it's not terrible news in the sense that most of these are still close to this line. And I got this by just saying multivariate plot is QQ. So this is a QQ plot. Yeah. QQ stands for quantile plot. So, any questions so far? I'm rushing through things perhaps at a quite quick pace, but hopefully it's all understandable. Yeah. So, solutions. What you could do if you find like really big deviations, if it had veered off, you could check for outliers. So likely you will find, especially these cases, these guys are the ones with really extreme scores. So they're really far away. So likely you have some outlier issues. So you could try screen for those outliers, like things which are 3, 4, 5 standard deviations away from the mean, or look at those box plots and see if you find stars, like things which are particular cases which are really far away in your analyses. You could run the analysis again, and then if you were transparent, you could say, here's the result with outliers, and here's the result without outliers. And people can make up their own mind. You could try and transform the data. So sometimes it's you have skew in your data, and that's causing the problem. So you could try to make things more linear. I've told you a little bit about log transformations, for example, to make things more linear in the first week. So if you have very extreme things like income, for example, a couple of people will really earn a lot of income, and to get everybody on the same scale, people often take a logarithmic transformation of that variable. And one of the transformations you could look at is the Box-Cox transform, which generally helps to make data more linear. So you can click there and find out more. And again, why am I not too worried? The central limit theorem is again to the rescue, because we have quite a big data. If we had 30 to 40 people, I'd be really concerned. But we have 200 cases, so the central limit theorem is helping us here in terms of multivariate normality, right? Because we have, as the data set increases and as the sample increases, our statistics will become more and more robust to violations of normality. So that's why I'm also not too concerned about that small deviation that we got on that chart. Now, homogeneity variance also applies. So remember, you have, for ANOVA, you have all the assumptions of the ANOVA, but then you have some bonus ones. So you would run a series of tests, like Levi's test, for every single dependent variable to see if it plays nicely. I've not done them here, but you can imagine. So we've done them for extroversion. You've done them for extroversion. I've done them for openness. So you would run 5 Levi's tests if you were to do this. So then there's a homogeneity of covariances. So we have homogeneity of variances and homogeneity of covariances. So quite a lot of assumptions for the ANOVA. You should approach this with care. There's such a thing as boxes M tests. It's very easily significant. So, and usually people actually say you should not use P is 0.05, but P is 0.001 for it to be a problem. Yeah. And you can read more about that again by that link. How do you do this type of box M test? We call a package. There's bio tools also which will do it, but we call HE plots, and then we do box M, the data set. And so this is the data set only with the dependent variables in it. And we say which type of variable is the factor influencing. Yeah. And so in this case, you could see it's not significant. So that's actually good news, because you should remember this test will be very easily significant. So we shouldn't be too much worried about homogeneity of covariances in our case. Yeah. So we've checked multivariate normality. We checked homogeneity of variance. We checked homogeneity of covariance. Now we can actually do our ANOVA. Yeah. And so in this case, the difference is in the M, and we use cbind to basically combine all those 5 things that go in front of this. So all these dependent variables go into this thing, and then we have our group factor, and then we can summarize the ANOVA model. You remember from your SPSS output, you get things like Peli's trace, yeah, and Heinfeld, and all these other things. So they will also exist in R, but Peli is the standard one. So we'll give you your F value, and we'll give you your P value. So a highly significant effect. So In this case, the groups differ in their personality profile on those five traits if we do a MANOVA. Any questions so far? And you remember this P-lie thing is a measure of effect size, which is used for MANOVAs. So other measures exist, but P-lie trace is the most commonly used thing to report. You can find more about Hohenfeld and Greenhouse Geyser and all these other corrective things which you might recall from SPSS. And you can also find out more about the math because they differ in how they apply corrections for example, violations of homogeneity variance. You remember things like Greenhouse Geyser corrected test. So what you write, again, P-lie trace is most commonly reported, and here we don't have any strong, I didn't do all the things, but I would just stick with the default here with P-lie trace rather than use Greenhouse Geyser or whatever. And so a sample report would be like a MANOVA was conducted with 5 dependent variables, and then you would list those: neuroticism, extroversion, conscientiousness, agreeableness, and openness to experience, and culture group as a between subject factor. And then you could write a statistically significant effect was found, and then you report the P-lie trace, the F-test, and the p-value. Yeah. So this is how I would write up this type of finding in APA style. Yeah. Any questions so far? And then what? Now the question actually leads to more questions, because then the question is, where does it lie? Is it openness to experience driving this, or neuroticism? So what typically happens is people do a MANOVA, they find an overall significant effect, and then they start looking at the individual ANOVAs. And the reason for doing a MANOVA is, again, to avoid this type 1 error where you would have something significant. So if we had started out by doing 5 ANOVAs to begin with, 1 would have been significant, and then we would have focused on that. This avoids by first seeing overall is there an effect, and then we go and look where the differences lie. Any questions so far? And so in conclusion, the personality profiles, you could say, differ between these 3 groups. So you would do follow-up tests. You could plot your data to sort of see how it's different for each group by making those histograms for each group and panel them. You could do univariate ANOVAs, and you could also do something which is more complex, which is known as discriminant analysis. Again, lots of different options. For some of the things I'm going to say, if your supervisor wants this, this is where you go and look for it. Yeah? And this is the end for today's lecture. So I only glossed over today type 1, type 2, and type 3 errors, but that will become more apparent when I talk about interaction effects, which will follow on, if I'm not mistaken, next week. So for now, you should just know that the order matters, and unless you specify that it's type 3 errors, you'll get different results because the default will be that it uses type 1 errors. In that case, the order in which you put things in the equation will give you different results. And so what I would like you to do this week is you can continue on using the dataset from last week. So that's the salaries database, where you get to see how much assistant professors earn, not here, but in the US. And you can see if it matters. And so you do the ANOVA with monthly salary as the dependent variable and academic rank as an independent variable. So do full professors earn more than assistant professors? I think you can also already guess what the answer is going to be. Then I would like you to use the post-hoc tests. What do you conclude? I would like you to use a non-parametric alternative to this. And then I would like you to have do an ANOVA with gender as a factor and year since PhD as a covariate. What do you conclude? Is it the case that after you control for how long people are academically tenured, that you no longer find a gender effect, or that you do find a gender effect? And then we're going to use a different data set to do the MANOVA. You're going to load the IRIS data set. It's a famous data set where people measured, it's quite boring perhaps to you, but biologists measured the 3 species of iris flowers. They measured the petal width and the sepal width and all these other things and lengths. So you run a MANOVA for that, and then you can plot one of the results for your analysis as a bonus, and you conduct a follow-up analysis for the MANOVA. Any questions so far? So next week I'll pick up and I'll tell you a lot more about type 1, type 2, type 3 errors and the difference. And then we're going to do things like interaction effects, because most of the time in psychology you'll face like interaction effects, like a person's behavior changes as a function of the environment. So that's typically an interaction effect, or modeled by an interaction effect. Any urgent questions? No? So Alex will stay along here for the next bit. And you should really, if you haven't done any exercise, try to catch up with the exercises, and then you'll see me in the afternoon because you'll see me again. It's a really sad day for you, but I'll tell you a little bit about open science and open science framework for Chris's lecture in the afternoon. But Alex will be here for another 45 minutes or half hour, depending on how long people need to be. But you don't have to be here. You can go for lunch or do whatever it is you want to do. Any urgent burning questions? And again, use the discussion board. Some people have engaged with it already, and that's where I'll try and answer some of the queries you have. There might be some things which I'm unable to resolve because they're very specific to your operating system or to the fact where the unit lets you write files, but I'll do my best to resolve what I can in terms of issues you might have with R and R packages. No questions? Everybody happy? So after today, you can cover ANOVA, MANOVA, and all these other sections from your assignment. So it's picking up quite fast, and so you're able, if you're coding along with the assessment, you're able to do large chunks already. And I think we have interactions left, and then correlation and regression and logistic regression. And then we have covered everything for your first assignment already. Okay.